Hello there. Welcome to our today's science lesson. The topic for the day being the periodic table of elements. A review for our previous lesson. In our previous lesson, we looked at the periodic table, some basic ideas on how the periodic table came into existence, the parts in the periodic table, which we found that though we have so many elements in the periodic table, but they are found in different parts or groups or categories in that very periodic table. And those groups or parts are based on the chemical properties of those particular elements. We saw some being metals, but even those metals are also grouped into various groups. We saw the transition metals, we saw alkali metals, alkaline earth metals, and so on. Today, I want us to look at what I gave out as an assignment in the previous lesson, which was to clarify on how a periodic table is made. Then today, we shall top up by now looking at the whole periodic table. You remember that you can get that what I gave you was just part of the periodic table for the first 20 elements. But after we have gone through that, we shall also look at now the whole periodic table and how it has been constructed to look the way it looks. Just as a reminder, we saw that for us to look at an atom, to use it in placing that particular element in the periodic table, we have to know that any neutral atom, protons and electrons must be equal in number. Protons and electrons must be equal in number. We also saw that this atom has what we call mass. Each atom has a mass, and for us to get mass, then it is just protons plus neutrons. Then we get the mass. Mass is equals to protons plus neutrons. But for us to construct a periodic table, our most important part is the number of protons, which directly or indirectly, the way you look at it, it will have given us the number of electrons. Once you know the number of protons, then you will have already known the number of electrons. But we also need to know that the number of protons, we also have what we call atomic number. Atomic number is the number of protons. So you look at atomic number, then we are just looking at the number of protons to that particular element. So these three statements are very key in us being able to construct a periodic table, and more so this one and this one. This one is only to give us the atomic masses of that particular element. But for us to construct the periodic table, then we need to understand the first one, which is what is this atom? The atom, so long as it's a neutron, its protons and electrons must be equal in a number. And you also need to know that atomic number is the number of protons, because in the periodic table, what is written there is atomic mass and atomic number. So if you don't know what atomic number means, then you can have it a bit difficult to arrange those elements. And lastly, the key point we also need to remind ourselves is after you have known the number of electrons, you have known the number of electrons to any particular element, atom of an element, then you need to write what you call electronic configuration. Electronic configuration, which is just a show of how many electrons are in which orbit, or what I also call energy level, because those electrons are arranged in a circular manner around the nucleus. So in that circular manner, each cycle, which is an orbit, has particular energy level. They are not of the same energy. That's why we also use the electronic configuration in terms of energy levels, or an electronic configuration in terms of orbits. Then, going by the first part I gave out, we saw that the first energy level, for us to get the electronic configuration, the first energy level can only be occupied by a maximum of 2 electrons. The second energy level can also be occupied by a maximum of 8, and the third energy level can also be occupied by a maximum of 8 electrons. And that is the assignment I gave. So I want us to go through the assignment and see what you did, if it falls into what we are supposed to have. Being that the maximum number of electrons to be occupied by an orbit is 8, it will give us 8 groups. So we start off to create the table. So we have 1, 2, 3, 4, 5, 6, 7, 8. Have it as 1, 2, 3, 4, 5, 6, 7, then lastly 8. Then in terms of the periods, I say these are groups or chemical families. We have periods. We are going to work with the 4. So we have 1, 2, 3, then lastly 4. May I have a double line here? We shall understand later on why. Because remember, this is just part of the periodic table, part of the big periodic table. So when I will be looking at the big periodic table, you'll understand why I'm having the double lines. So you can have this one as 1 or 1. You have to be keen that when you are labeling the groups, this is the format of writing or labeling, and when you are labeling the periods, this is the format 1, 2, or 2, 3, or 3, then 4, or 4. Now, just to remind ourselves again, for us to get the number of periods, these are periods and these are groups. For us to get the number of periods, you only look at how many orbits have been occupied. If you occupy one orbit, then you talk about period 1, 2 orbits, 3 orbits, and 4 orbits. Then for the groups, you look at the number of electrons in the outermost orbit or in the outermost energy level. If it is 4, then you will come and place it in 4. If it is 7, you look for 7. So you first of all check on how many orbits, then outermost number of electrons, how many they are. So let's look at the first 20 elements, but not in order. I'm going to write the first 20 elements, which I'm not going to place in order, so that from that I will give the atomic numbers. Out of the atomic number, we shall get the electronic configuration, and out of the electronic configuration, we can come and arrange the elements in the table. So here are the elements. we have 1, so 2 is missing. Need to have change to this. We have 1, 2, 3, 4. Can have here a 5. Six is missing. Can have a 6 here. Have 7, 8. Can have now a 9. Ten is missing. 11 is there. 12, 13. So that I can have now my 10 here. 11, 12, 13, can have 14, 15, 16, 17, we have 17 here, 18, so 15, 16, 17, 18, 19, 20. So let's go through and see if all the elements are present. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So those are the first 20 elements that I would wish we now make a periodic table out of this. I've arranged them haphazardly so that we can see if we can rearrange them following the electronic configuration to fit into the table that we shall now confirm with our periodic table here. We arrange, then at the end we shall confirm in relation to the periodic table. So let's start off. So let's start with the 1, and that is hydrogen. Hydrogen is atomic number 1, meaning that it only has 1 proton, implying that only 1 electron, and being 1 electron, then our electronic configuration will just be 1. What does this 1 mean? 1 means in terms of orbits, it's just 1, and in terms of how many electrons are in the outermost orbit is again 1. So the only place we can fit here this hydrogen is at this point where it has 1 orbit and 1 electron in the outermost energy level. So we can have our hydrogen at this point, hydrogen. Then secondly, we have lithium. Our lithium has atomic number 3, meaning that it has 3 electrons. So to write our electronic configuration, it will be, this one was 1, it will be 2, because first energy level maximum is 2, the remaining is 1. What does it mean? We have 2 energy levels or 2 orbits. So 2 orbits, that's the point. Then outermost we have 1 electron, which means here. So the point becomes at this point 2 energy levels, 1 electron in the outermost orbit. Our second element is third element is sodium, which has 11, meaning that electronic configuration first energy level 2, remaining 9, add 8, 10, so we haven't reached 11, so the remaining becomes 1. So it is giving us how many energy levels? 3. Outermost 1. Energy levels 3. Outermost 1. So here we have our sodium. Let's look at the next one, that is magnesium, which has 12. Electronic first 2, then 8, remaining, that is 10, 12, remaining 2. So energy levels 3, 3, and outermost is 2, 2. So the place is at this point. Our next one is calcium, which is 20, implying 2, 8, that is 10, another 8, that is 18. We haven't reached 20. 18 to 20, from 20, remaining 2. So energy levels here are 1, 2, 3, 4. So 1, 2, 3, 4, this is the point. Outermost 2, 2. So here we have our calcium. Move to the next one, we have 19 for potassium. 19. 19 here implies 2, 8, that is 10, 8, that is 18, remaining 1. Energy levels 4, outermost 1. Here is potassium because it has 1, 2, 3, 4, and outermost is 1. Next one is 17 for chlorine. 17 meaning 2, 8, that is 10. If I write 8 here, it will be 18, and here we have 17. So remaining 7. So that we have a total of 17. Meaning energy levels, there are 3. 1, 2, 3. 3 is here. Outermost 7. 1, 2, 3, 4, 5, 6, 7. So this is the point. 7, 3. They come and meet at this point. Chlorine. So move on. We have our next one is 8 for oxygen, which gives us 2. I cannot have an 8 because it will be 10. Maximum is 8. So the remainder is 6. How many energy levels? 1, 2. Outermost 6. So 1, 2, 6. And here we have our oxygen. Then the next one is nitrogen for 7, 2, remainder 5. Energy levels 2, outermost 5. 1, 2, 3, 4, 5. 5, then 2. And here we have our nitrogen. The next one is beryllium. Beryllium for 4, giving us 2, remainder 2. Energy levels 2, outermost 2. So 2, 2. And here we have our beryllium. Next is helium, which has 2. And first energy level 2. And they are all done. So how many energy levels? 1, outermost 2. This is a point of concern. And I need us to understand the concept behind this. Now, if I can use an example of 2 children or 2 individuals, one is a child and another one is a mature person, they are all having a meal. And this meal is enough for each one of them to say, "Thank you, I'm satisfied." Do you think the small child and the mature person will eat the same amount of food? I think the answer is no. They will eat different amount of food. The child will have a small amount of food, but at the end, the child will be satisfied. The mature person will also be satisfied, but will have to take a bigger amount of food. So, when you look at the first energy level and the second energy level, or the first orbit and the second orbit, for you to say the first orbit is full, you only require 2 electrons, and it is full. You will not call it a half. You will call it a full orbit in terms of the electrons that are present in that orbit. For the second one, you will have to get 8. Even if there are 7, you cannot say it is full, because for it to be full, it requires 8. And here you are talking about less than 8. Even if it is 7, 6, or 5, they will not be full. But for the first energy level, you will say they are full, even if you are talking about 2. Now, this aspect is coming out to explain the part of this helium not being placed at the point of where the outermost energy level electrons are to, where it should be among the beryllium, magnesium, and calcium. That is not the point we shall place it, but we shall place it at a point where it will be said to be full. Just like if you ask now the individuals and you ask those who feel they are full, they have eaten, they are satisfied, the child will carry up the hand, and even the mother or the father or whoever the mature person was eating with the child will also carry up the hand and say, I'm equally full, and yet they have eaten different amount of food. So the same case here applies. So we shall place this helium in a group of elements or at a point where the outermost energy level is full. And here is where we have 8, because the outermost we require is 8. Maximum is 8. You can see once you reach 8, you go to the next one. You reach 8, you go to the next one. It means you are full. So because of that, helium will not be placed at this point, but the correct point it will be placed is here. Reason being, this is a group of elements that have their outermost energy level full. But it has how many energy levels? Just one. So one energy level or one orbit, but outermost is full. You don't look at the two, you now look at it being full or not being full. This will also be used to explain why this element hydrogen also has some unique characteristics. Remember, when we look at this periodic table, we saw this hydrogen being in group 1, but having a color of nanometals. So this is the point we need now to clear the air and know why that was the case. Hydrogen is in this group 1 because, as you can see, and that's why I arranged them in order so that you can see the sequence, it is having 1 electron in the outermost energy level like lithium and sodium. So because of that, it shows some characteristics similar to lithium, sodium, and even potassium, which also has 1. However, you also need to realize that it only has how many energy levels? 1 energy level. So being 1, a maximum of 2 electrons. That 1 energy level, maximum of 2 electrons. But it is only having 1. So if you remove the 1, how many are missing to make sure that the outermost orbit is full? You only require 1. So because of that, it can also be placed in a group of those elements missing only 1 electron to be full, and that is in group 7. Group 7, which we called halogens. If you look at chlorine here, it is missing 1 electron to reach 8. So hydrogen can also be placed in this category of elements where it is missing just 1 electron. Missing just 1 electron, you add 1, then you will get 2, and 2 just like helium. And if it is that's the case, helium we have placed it in group 8. So it will also be nearer that. So hydrogen can also be placed here. This explains why you may find in some books the hydrogen element has not been placed in group 1, neither has it been placed in group 7, but has just been placed at the center of the periodic table, because this is like an element that doesn't know where it wants to go. It wants to be in group 7 because it is missing 1 electron to be full, but it also wants to be in group 1 because it has only 1 electron in the outermost orbit. So hydrogen, you'll find in some books, it is being just placed at the center, and that is the explanation. So we can proceed. Now the next one is boron. Boron has 5, giving us 2, then 3, 2 energy levels, 3 outermost. 2 energy levels, 3 outermost. So we have boron here. Then next is carbon with the 6, giving us 2, 4, 2 energy levels, 4 outermost. 2, 4 outermost. Here we have our carbon. Then there we have fluorine, which has 9, giving us 2, remaining 7. So that is the same category as chlorine and the same as hydrogen, as I've just explained. Hydrogen, chlorine, and fluorine are in agreement in a way. So here we have 2 energy levels, 2, then 7 outermost. So here we have our fluorine. Then we move to aluminium, which is 13, giving us 2, 8, that is 10, remaining 3. Total 3 energy levels, 3 outermost. 3 energy levels, 3 outermost. So here we have our aluminium. Move to our neon, which is 10, giving us 2, then 8. Complete. So total 10, 2 energy levels, 8 outermost. 2, 8. So here we have neon. That makes our second noble gas, next to second to helium, which has also 2. You can see helium 2 was full, and you also have here neon, which is full. We'll now move to silicon, which is 14, giving us 2, 8, that is 10, remaining 4. So 3 energy levels, 4 by group. So we have silicon at that point. Then we have sulfur, which is 16, giving us 2, 8, that is 10, remaining 6. 3 energy levels, 6 outermost, 3, then 6. And here we have sulfur. Then we have, let's look at our next one, which is argon. And argon here is given by atomic number 18, meaning that 18 protons, 18 electrons, giving us 2, 8, that is 10, remainder 8, 18. So giving us 3 energy levels and outermost 8. 3 energy levels, outermost 8. So we have our argon at that point. Argon is written at that point. Then lastly, we have our element as phosphorus, which is 15, atomic number of protons 15, electrons 15, giving us electronic configuration of 2, 8, that is 10, remainder 5, giving us energy levels 3, outermost 5. Energy levels 3, outermost 5. And that is our phosphorus. So looking at the table we have just constructed, let's check and see if we have done the right work. And that can only be done through a comparison. And the comparison is the table we have made in relation to the one we saw having all the categories of the elements. So this one is giving us the first element as hydrogen, and here our element is hydrogen. Second element is helium. We also have this one as helium. Haphazardly, if I can choose, for example, element number 7. Number 7 here is 1, 2, 3, 4, 5, 6, 7. 7 here is nitrogen. If I can also check on number 7 is nitrogen. Maybe let me pick on number 13. Number 13 means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 here we are seeing aluminium. Do we have aluminium in the same position? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 here is aluminium. So using those 3 examples, I can ascertain that what you have done is very similar to what we have in the table here. But remember, this is just a fraction of the big periodic table. This takes us to why do I have the double lines in that periodic table. So this double line, I only wanted to show you that there's a part that we haven't introduced in this table. And that part is the blue region, which is carrying what we call the transition elements or transition metals. In these transition metals, again, we also have a point where we call the lanthanoids and actinoids. There are also so many elements that have similar characteristics. Because there are so many and cannot be fitted in one particular point in this periodic table. Now, looking at this periodic table, the big periodic table, I've said that we have the blue region, which we call the actinides and lanthanides, but they cannot fit in the one box we have here and this one. So they are expanded to this point. So these are the lanthanoids and these are the actinoids. 15 of them, they are supposed to be fitting at this point as lanthanoids, and 15 of them which are supposed to fit in actinoids. But in terms of the arrangement, it will just be understood as I will be looking at how now the big periodic table is arranged, again just following what we have done for the small one in terms of the electronic configuration. So we have to understand that the double lines in our small periodic table is to take care of this blue region, and this blue region also has an inclusion of the lanthanoids and the actinoids. Having seen the transition elements, which is a very important component of the periodic table, we now need to understand on how they are arranged the way they are arranged in this periodic table, the big periodic table. To understand that, let's look at the electronic configuration that will cover from the first element to the last element. Remember, we learned in our previous lessons that we have about 118 elements, and out of the 118, we have 92 that can be found at any single moment one may wish. But the others have a short lifespan, what we call half-life, so they occur at very limited times. But they are there, giving us a total of around 118 elements, active ones that can be found everywhere, 92. So I want us to look at another additional electronic configuration, which is now going to help us arrange other elements past now the atomic number 20. It is now from 21, and 21 is the beginning of the transition elements. So the electronic configuration we have seen is the first energy level can take a maximum of 2 electrons. The first orbit taking a maximum of 2. The second orbit takes a maximum of 8. The third orbit takes a maximum of 8. The fourth orbit takes a maximum of 18. Fifth, 18. Sixth, 32. And the last one also takes to 32. So with the second 32, all the elements in the periodic table will have been taken care of. Now, just to confirm that this is true, you realize that we have been talking about 8. How do we reach 18? Can these groups or categories of transition metals or elements fit to make us move from 8 to 18? Let's confirm. They have groups of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I have 8 and I add there 10, you can see we are getting 18. So it is very much in agreement with the periodic table, so that when you have your previous 8 plus now the present 10, it will still take you from 1 to 18. Now this explains why our periodic table has 18 groups or 18 columns, and that is, let's confirm, if there are truly 18, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the periodic table has 18 columns and 7 periods. 18 columns and 7 periods. One can easily ask, why choose 18 and not 32? And yet we can see from our electronic configuration, we have up to 32. The 32, we are avoiding, the 32 was avoided because to reach the next 18, so that because when you have 32 minus 18, that is 17, it gives us, that is 14, subtracting that is 12 minus 8, that is 4, 1, that is 14. Now, to get the next 14, to add on 18 so that you can get 14, how to explain this is done using the lower 2 lines. That is a line for lanthanoids and a line for actinoids, which is having 15 elements. We counted in our previous lesson and there are 15, but here we are getting 14. So how come this is 14 and this one is 15, and yet they have to fit into this so that you can get a maximum of 18? The one box to make us 15 so that it is equal to this one is the box that is written in 57 to 71 for lanthanoids and 89 to 103 for actinoids. So that box is there, but it's not having one particular element. It is having all of them. So minus that, plus that box, then it takes us to 15. For us not to go for 32, the actinoids and the lanthanoids are removed in the transition elements arrangement. They are arranged in their own order just below the big skeleton of the periodic table. But still, they have been indicated in the periodic table as this is the region where they occupy, and that is from atomic number 57 to 71 for lanthanoids and from 89 to 103 for actinoids. So their atomic number have been allocated, but the elements themselves do not appear in the big periodic table. So they are part of the 100, like in this periodic table, they are working with the 112 elements. So they are a part of the 112 elements. Their space has been shown. Now, let's confirm or prove that surely this is the electronic configuration that is used to arrange these elements to form the big periodic table. I think it will be so much exciting because it really makes you feel confident that you know how the periodic table has come into being. Just what Mendeleev, the first scientist to look at the periodic table, started arranging the elements, but was not so perfect. But right now you can perfectly arrange the elements in order. So let's start off. We shall avoid this part because we have already done it, and in fact even in the 18 we already have potassium and calcium already covered. That is in the 4th energy level or in the 4th orbit. We have already covered 2 elements, and that is potassium and calcium. So we shall pick on any elements in this other area and confirm what we shall have gotten and what we have in our table. So let me pick 3 elements from the transition elements, that is in the blue region. I can pick vanadium, Vanadium as an element, electronic symbol, capital letter V, atomic number 23. As I said, the most important number is atomic number when you want to arrange the elements in the periodic table. So atomic number 23. Let's look for its position using electronic configuration and see if it will fit where it is placed in this one. So we have 2, 8, that is 10, 8, that is 18. We are now at this point. Now we need a maximum of 18. Can we get there? At this point we already have 18. We will need to go to 23. How many are we missing? So we have 23 minus 18, and that one gives us 5. So we have here 5. Is it true? That is the point. Let's confirm. So we have here as 1, 2, 3, 4, 5. That's the point. 1, 2, 3, 4, 5. So at this point it shows that we require 5 electrons in the outermost orbit. We have it. Do we also have it having 4 energy levels or 4 orbits? That is 1, 2, 3, 4. Does it have 4 orbits? Let's see. First orbit, second, third, then fourth. So you can see it is here. So it is a 4th orbit and 5 electrons in the outermost orbit. So it has qualified. Remember, this is a transition element. Let's pick on a bigger one. A bigger one like, we always talk about gold. When you perform very well in an activity, you are given gold. Let's talk about gold. So we have gold, known by almost everybody in the world. So we have gold. Gold is written as Au. Now gold has an atomic number 79. Atomic number 79. Let's get the position, confirm it. So with the gold, we have now 2, 8, that is 10, 8, 18, 18. Let's see, 18 plus 18 gives us 36. Not yet. Remember, we have to go up to 79. Another 18. Let's add the 18. So we get 54. Are we at 79? Not yet. We add there 32. 32. That is 6. 86. We are past 79. So we cannot add there 32. So then what are we supposed to add there? So we get it at 79 minus 54. This one gives us 25. So instead of 32, at this point we require 25. Now, with this 25, remember the maximum columns are 18. The maximum columns are 18. But here we are talking about 25. How do we handle that? Remember, we have actinides and lanthanides. Once you are in these 1, 2, 3, 4, 5, 6, when you are at energy level 6, then remember we have lanthanoids and actinoids. When you are in the category of lanthanoids and actinoids, you have to add their, subtract their 15. Remember, there are 15 of them. 15 of them. So here we get now 0, 10. We move at point 10. But this point 10, remember, there is a box that lanthanoids or actinoids, there's a box that lanthanoids and actinoids are occupying, which is 1. So the exact number you are supposed to subtract here is, also you have to subtract the box. Or depending on how you will count. If you will count including the box, you leave it that way. If you will count minus the box, then you have to subtract 1. So the best is, let's count subtracting the box and see the position of gold. Or we subtract 14 and we get here 11. They are all the same. So long as you remember there is a box that is in the table but does not have a particular element. Instead, it has elements which are either lanthanoids or actinoids. So if we can work with the subtraction of 14. Now let's see 11. 11 we have, it is in 1, 2, 3, 4, 5, 6. So it is 6. Remember it is 25. But remember the 25 is beyond 18. We work with the 11. So 11 outermost energy level electrons. 6. 1, 2, 3, 4, 5, 6. This is the point. So at this point 6, now we move 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. Now I'm counting 11 because the box that was missing, I've included the box by subtracting 14. If I subtract 15, that is all the 15, then it means I've subtracted the box. But if I subtract 14, then it means I've included the box, and this is the box here. I've included this box in counting by subtracting 14. If I subtract 15, all the 15, then it means I will have excluded the box. Just to recount, 1, 2, 3, I'm including it. 4, 5, 6, 7, 8, 9, 10, 11. And 11, this is the point where we have gold as an element. Having confirmed the 6 and 11. Unaona, hiyo zooming elephant ya kwanza hiyo is enough because they will be always going back to that point. Si atu zoom ukiendelea. Now that was gold. Let's have another third example. We can even pick the third example outside the transition elements. The transition elements, may I pick maybe an element which is an nonmetal, or even now a noble gas. Let me pick on radon. Radon is here. This is radon. And see, are we going to get this position of radon? Radon as an element has atomic number 86. Radon has 86, giving us 86 protons, meaning 86 electrons. Therefore, let's get the electronic configuration. It will be 2, 8, that is 10, 18, 8, then 18. Then from 8, the next is 18. So 18 plus 18 giving us 36. Then from 36, we add another 18, giving us 54. Still, we are not yet at 86. So at 54, at this point we are at 54. If we add there another 18, where are we? That is 12, 6, 7. Still not there. Can we add now a 32? Because remember we have covered our 18 to this part. Our next one is 32. If I add there 32, can I get it? 6, 86. There we are. You add there 32, you get 86. 86, it means the maximum. 32, if you add there 32, that's the maximum. Or if it is this energy level, maximum is 18. This level, maximum is 8. This level, maximum is 2. So we have added there maximum 32, and we hit our 86. But we have added 32, and yet our maximum is 18. How do you explain that? just like we did for gold. You remember the actinoids and lanthanoids. So this one, do we talk of lanthanoids or actinoids? It is in 6. We are talking about lanthanoids, not actinoids. Actinoids is the last one. So we have now to subtract from 32, we subtract 14. 14 means you are including that box. You are including that box that is carrying the explanation of 57 to 71. If you subtract 15, when counting, you exclude that box that is carrying the information 57 to 71. But it's always good to include. So you subtract 14. So this one gives us 8, 2, that's 1, 18. So we count 18 boxes. 18 boxes in energy level number. So this one is 32. Energy level number 1, 2, 3, 4, 5, 6. In energy level number 6. So let's look at 6. 1, 2, 3, 4, 5, 6. So we start off 6. 18 times 1, 2, 3. We include this box. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There we are at radon. Now, radon as an element in the last energy level, in the last group, it is among what we call the noble gases. As you can see, that is how the periodic table is constructed. Just identify the atomic number, which gives you the number of protons. Number of protons gives you the number of electrons. Number of electrons gives you the electronic configuration, and the electronic configuration gives you the number of energy levels, and in addition gives you the number for electrons in the outermost energy level. In addition, you need to realize that once you are talking about energy level 6 and 7, where we have lanthanoids and actinoids, you have to remember to subtract 14. You have to remember to subtract 14 or 15, the way you will understand best. When you subtract 14, when counting to get the position, you include the box that is carrying the information of which region or which range is for lanthanoids and actinoids. When you subtract 15, the figure you get will be minus the box. If I can just use this radon, if I subtract 15, it will give us 17. So when it comes to 17, when counting, you will skip this one by saying 1, 2, 3. I've skipped now this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. But you see, by using 15, it can easily cause a confusion because you have already been tuned to 18, but here you are counting 17. So it gives out a bit of a confusing point. So it's good always to subtract 14 so that when counting, you include the box. So just a review of the lesson. Periodic table is a very important aspect in science, particularly chemistry, because it is the summary of all the elements that will be interacting with in all the lessons to do with the science. And since this is an important aspect, you need to know how it came into being. Starting from the early years of Mendeleev, he struggled so hard so that you can get coherent information on how the table is made. Then a summary on how it is made came out to be, you just identify the number of protons, which gives us the atomic number, and the number of protons gives us the number of electrons in any neutral atom. Then the number of electrons will give us what we call the electronic configuration, which, for example, it's this one. And in this electronic configuration, you have to follow rules. And the rules are the first energy level or the first orbit, maximum 2, the second and the third, 8, the fourth and the fifth, 18, and the last 2 is 32. And lastly, in these last 2, we have a special type of group of elements called lanthanoids and actinoids. Being that there are so many, 15 of them in a number, but having same type of characteristics, they can easily be put in one box because of the characteristics. But you cannot just put 15 in one box and it remains that way. No. Even if they are the same, they may have some small details that are different. Because of that, they are arranged just below the big box or the big table as lanthanoids, the first ones, and actinoids, the second ones. But when it goes to the big table, they are placed in one box. Placed in one box as lanthanoids, as actinoids, at the bottom point of lanthanoids. Arranging all those in the periodic table, you now come up with our beautiful table, which is very helpful. And as we proceed with our science lessons, you will discover how helpful it is. And it is from this table that one can easily pinpoint the most important element to perform a particular activity, because you just have to identify the characteristics, look for a group that has similar characteristics, and there you are, you have gotten the element. That marks the end of our lesson today. Thank you.